Okay, they said write the overall equation for the Lebesgue process, right? So potassium chloride is a crystalline solid used in fireworks. It's produced by the Lebesgue process in two stages. You have stage one, where you can see clearly the hot calcium chloride, basically hydroxide solution is forming the calcium chloride 5 CaClO3 2. And then again in stage 2, the potassium chloride solution is then added to produce the potassium chloride 5. So that's the reaction with the product produced in stage 1. And then the remaining three steps are done, where the solution is heated to reduce its volume, then allowed to crystallize, while the crystals are then filtered out once the crystallization process is complete. And then last, the remaining filtrate is evaporated to further obtain more crystals. Do you know why the third step is done? Like, how can you do the evaporation of the remaining filtrate, Simra? Any idea? Sorry?
You dry basically, right?
Yeah,
So that any remaining solution on the crystals are removed.
yeah, kind of, you can say. Off, off, টেলিগ্রামে দিচ্ছি দাও. Okay, let's start. Uh, so there to write the overall equation for the Lebesgue process, isn't it? So if that's the case, that means what does it mean? So basically, we need to just involve both of the equations provided down here, and then just cancel out the spectator ions so that we can get the the original one or the final version, the simplified version, basically. So what do we have here? Okay,
Separate CaOH.
okay, if you check out down here, so if you just just add these the reactant the reactants together, what comes? So you have 6 CaOH2 plus 6 Cl2. Okay, then comes then this two get cut, right? Because this two will get cut, so eventually only this one remains. So plus 2 KCl. Then when you do the next part, the product side, here we have KClO3 left, and there is what there is basically one CaCl2 with addition of 5 CaCl2, that will be 6. So that will be 2 KClO3 plus 1 and 5 will be 6 CaCl2. And do we have anything left? Yeah, the only thing that's left is water down here. So plus 6H2O will be your answer. This is the required equation. Did you understand? What did we do down here? I just
Cancel the common.
Yeah, exactly. Like basically just cancel the common ones. That's it. Nothing else. I could show you in a more refined process by writing the equations down like this, and then uh, just draw like this. It's best basically if you write both of the equations like how you used to do addition back in kindergarten, and then you can just cut the common ones in both sides and then just write the final one like this. Anyways,
For CaClO3 too, one of them's on the product side, the other's on the reactant.
yes, exactly.
Just cancel them out.
Yeah, just how I did, you can cancel it out to ensure that you carry less space during the exam. It's more better rather than writing both of the equations here and then doing it. It's more of a hassle. Okay, now calculate the overall atom economy by mass for the production of potassium chloride 5 KClO3 in the equation. So what is atom economy, by the way? First of all, you tell me. It's basically molar. In the numerator we have what? The molar mass of the desired product divided by the molar mass of the total products, isn't it? Mr of desired product divided by total Mr of products, right? Times 100. So in this case, who is our desired product? KClO3. What is the molecular mass of KClO3, by the way? If I'm not wrong, it's about 122.6. That's what I get, gram per mole. Do you get that? Please check. And what are the like the next part is obviously we need to check out the reactant part down as the product or the summation of the molecular mass of all the products. So that's 122.6, that's 18. What's CaCl2 again, can you please tell me? mm, I'm not sure. CaCl2, check. Is chlorine 71? Hmm. Hello, hello, are you hearing me?
Green is 71. Chlorine is 71.
mm,
71. Can you hear me now?
yes, I can hear you, but wait, let me check it out whether there's an issue or not. Chlorine is 71. Fine. 1 minute. Oh, we also need to check out the moles present down here. Okay. So we need to multiply 2. Then here it will be 6 times 18 plus, I mean, that's 18 obviously, 18 gram per mole. No shit. And CaCl2 will be 71 plus 40.9, right? Times 2. I think I made a mistake. So 40.9 plus 71 times 2, isn't it? What is the answer? 40.9 plus 71 times 2, that would be 182.9. So 1 mole is about 182.9 gram, right? So what will be 6 moles? So 6 times 182.9, and then obviously the that one 2 times 122.6. Now if you just do the 100%, what will be the answer? 202.6, 6 times 18 plus 6 times 182.9, 2 times 122.6, that would be do you get 16.9? Hmm. Yeah, 16.9%. I believe that should be the correct answer. Wait, let me just double check once. No, no, yeah, it's okay. Makes sense. Also basically depends on the overall equation. Okay, without the overall equation it's kind of tough to find the atomic economy. Otherwise, I mean, your process will be correct, your product might be the final answer might be wrong. So ensure that your overall equation is balanced. Okay, because we are going to use the stoichiometric coefficients in order to find the atomic economy. Moving on. B, right? Do you have any other problem? C part 2. 1.252 gram of potassium chloride 5, they said that formed in the Liebig process. So this much amount was heated until the mass of the solid remaining was a constant at 1.02 gram. The reaction that occurred was this decomposition right here. The impurities present did not decompose on heating. Okay, sure. They told you to calculate the percentage impurity, right? You want to calculate the percentage impurity. Okay, let's start. Let's find the mass of oxygen first. How can you find the mass of oxygen? They said here that 1.52 gram basically what was, well, this initially it was 1.52 gram, and after decomposition it was 1.02. So can't we easily say what will be the oxygen of oxygen mass? How much went out, isn't it? 1.52 minus 1.02. Did you understand what I'm trying to say? Like, the remaining solid will be what? Obviously the remaining solid is going to be KCl, right? 1.02. So I mean, the remaining solid will be KCl along with the impurities, considering, because they did not say the impurities did not decompose on heating, right? So in this case, if we just subtract this from this, we will be able to get the oxygen mass. Pure logic. So how much is that? That will be 0.50. Okay, now we can find easily the moles of oxygen, which is, can you please tell me? 0.50 will definitely divided by 32 is going to give you what? 0.015625 mole. I think we have made the moles of oxygen clear. Now, if you can you calculate the mass moles of potassium chlorate now? I think we can, right? How can you do that? Any idea? We can use the stoichiometric equation. Yeah, we can use the stoichiometric equation around here. So we know that 3 mole, I think the ratio is 3 to 2 here. So 3 moles provide you this much. So 3 moles provide you 2 moles of KCl3. Sorry, yeah, sorry, KClO3. So what will happen? So this much will provide how much KClO3? Can't we do it? So moles of KClO3. This is pure unitary method. Did you get my point? Or do I have to show you? Times 2 by 3. I think we made it clear. Yeah. If you want, so this will be the amount of moles. So if you just multiply the mass, sorry, if you multiply the molecular mass, then you'll also be able to get the mass, right? So instead of just writing finding the moles, let us also let us directly find the mass. So what will be the molecular mass of KClO3? Can you just find it out, please? I believe it's 74 point something. How much is it? 71 plus 16 times 3 plus k. What is the mr of k? How much? 29.1. So that's basically 74.4, right? So 74.4 gram per mole, and that is our obviously mole. So eventually you are going to get our mass. What will be the answer if you just do the whole thing? I believe it's 1.277 gram. 1.277 grams. So we got our mass of KClO3, isn't it? Hmm? Oh wait, did I make a mistake? I think I made a mistake, right? I think it's 0.77. Sorry, 0.777 gram, right? So this was basically the mass of potassium chlorate. Yeah. What did they say again? They said here to calculate the percentage, the
So you want to
impurity.
find the mass of impure
Hmm.
as well.
Yes. Okay, so what is the total impure sample mass? It was 1.52 gram. 1.52, 1.52. We are trying to find this one, isn't it? Don't think about KCl. This is the mass of solid 1.0. That is what this one. Get my point? What I'm trying to no, it does include, but they told you to find the percentage purity of the sample basically. Okay, so let us at first try to find the potassium chlorate one. Oh wait, did I? Sorry, you're correct. I think I made a little mistake. No, so far we found the mass of KCl, not KClO3. KCl basically. Sorry. Okay, this also includes impurities. I told you that time a little while ago. I think I little got jumbled. Okay, now it kind of makes sense. Sorry. Mm. So what will be the total mass left? We already found what oxygen's mass, right? So total mass would be 0.777 plus what's that? 0.50. So this is it. How much is that? I think it's 1.277. 277, right? Yeah. So this is like the mass of the whole thing in the sample after the decomposition takes place along with the impurities. Okay. No, I mean in impure sample basically. Yeah. Okay. So what will be the percentage purity then? The percentage purity is that our total impure sample was 1.52 gram. Okay. So out of this 1.52 gram, the only pure thing was these two down here, right? These two are the only pure thing. Forget the impurities. Impurities are there, you can't remove. These were the two only pure thing which we found the total mass of it. The pure things, the total pure things mass what was 1.277. So if you just keep 1.277 in the numerator and place the total impure samples mass, so eventually what will be the purity of the sample? The purity of the sample,
4.01.
yeah, kind of 84.01%. That will be the purity of the sample. So they're trying to say that it's 84% pure in one sense. Did you get my point? Like, did you understand the ratio? Basically, you write the the total mass of the pure sample divided by the total mass of the impure sample times 100. So that's how you basically get purity sample. In other words, they're trying to say this ratio basically represents how much of a pure sample is present in a mixture of an impure sample. Did you get my point? That's what the ratio claims. Anything else?
No, everything else is okay.
Samya, any you, do you have anything?
No.
So we'll move on to the next chapter today, which will be, of course, this one down here. Uh, Organic chemistry, halogen spectra. This is the fourth chapter, I believe, the last chapter, basically. Organic chemistry. Okay. This question, I believe it's the most easiest chapter in AS, in my point of view. I think it's so easy. Literally, 50 or 40% is previous knowledge from IGCSE organic chemistry, and while the rest 50 to 40% is about new stuffs. For example, mass spectroscopy, infrared spectroscopy. Then you have anything else topic new, the organic techniques basically. That's basically unit 3, but some of it you will get in unit 2 as well. So I would say organic chemistry is kind of easy in AS level. At least A2 is a different ball game. It's one of the easiest chapter. uh, what do you think the most two easiest chapters are? Both. Simra, tell me, in your point of view, which two chapters do you think are the most easiest? Eh,
Edexcel.
kinetics, and
Yeah.
only kinetics and nothing else?
Six and unit one. Entirety of unit one.
Okay, entire unit 1. Samya, what about you? Which two topics do you think are the most easiest in AS chemistry?
Unit one and Halogenoalkanes.
Exactly. I believe intermolecular forces, kinetics, and organic chemistry. These three are the most easiest in my point of view. Others might be a little bit tough, but these three are the most easiest. So my suggestion would be that uh, if you want, you can lose marks in the other chapters, but do not lose marks in these mentioned chapters, because these are like, I mean, regularly they provide standard easy questions from these chapters, what I have seen basically from the recent papers. Okay, so let's start. The question is about alkenes. Which of these alkenes is the highest boiling temperature? Now we have butane, we have hexane, we have pentane, we have propane. Okay, boiling temperature is related to intermolecular forces of attraction, isn't it? Right? Hmm? Isn't boiling temperature related to intermolecular forces of attraction? So can you please tell me what are the intermolecular forces present here? Anyone? London forces, exactly. London forces or dispersion forces, whatever you name it, basically, that guy is present. Now, how can you increase the London or dispersion forces? It depends on two factors. We all know that: chain length, branching, and what? Number of electrons, right? Now, branching means what? If there is more branching, surface area decreases or increases? So surface area decreases between the adjacent carbon atoms. And if I talk about number of electrons, force of attraction increases or decreases? Increases. And what about chain length? Well, chain length is kind of directly related to number of electrons. So number of electrons increases, so obviously you get the point. Force of attraction will also increase. Okay, butane, hexane, pentane, propane, all of them are of the same homologous series alkanes, and secondly they do not have any branching, so this factor is out of the equation. Let's move on to chain length and number of electrons. We can clearly see that the chain length is different. So the higher the chain length, our third factor is also related with the first factor. So higher the chain length, higher the number of electrons, so force of attraction will be higher. So who has the highest chain length here? I believe hexane, right?
Excellent.
So that guy will have the highest boiling temperature among others. Pretty simple, isn't it? Now, which of these alkanes has the lowest boiling temperature? Right now, I have explained you the three factors which affect the boiling temperature. So can you please now tell me which should have the lowest boiling temperature? Not Simra, Samaya, please try.
A.
A. Okay, why? Give me logic.
Particle branching nature and
Okay, very good. They are branching more. That means surface area decreases between the adjacent carbon atoms, and as a result, the breaking of bonds becomes much more easier, isn't it? So that's what it happens. A is the correct answer. Simra, did you understand? Okay. So I don't think I have to go through, because you can clearly see D will be always out of the equation considering it's a straight chain branch among all of the four. Now, if I talk about C and B, we can clearly see that this is the longest chain and this is the only branch here. So that will be out of the equation. Again, if you see, check out this one right here. Longest chain, only one branch. That will be out of the equation. So the only thing that's left is A, where we see a second branch. That's the reason A is the correct answer. Okay, let's move on to the next one. Which solvent dissolves the greatest amount of hydrocarbon? C35H72. Is this an alkane? Hmm? Or it's an alkene? Obviously, it's an alkane, right? Because if you use the CnH2n plus 2 formula, which is the general formula of alkane, I believe it's an alkene. You can check it out. Yes, we can, right? Now, question is, which solvent dissolves the greatest amount of hydrocarbons? C35H72. Okay, we have our four options down here. Can you tell me, it all look, the reaction or the solubility? Remember one thing, it all depends on the bond polarity. Can you tell me which one contains polar I mean, can you tell me which one contains polar bonds here? Okay, water is a polar molecule, right? It's a polar molecule, isn't it? So since what, okay, do you think alkanes are polar molecules? Think. No, they're non-polar. They're non-polar. There are two ways you can approach it. So polarity is one way you can basically determine solubility or reaction, and there is another way. That is what, this common nice rule, like versus like, or basically in other words, like dissolves like, or unlike doesn't dissolve like. These are like common analogies you can basically remember for understanding. If you use this type of concept, then it kind of becomes easier. So our answer will be C. You get my point? What I'm trying to say, because it's an alkane. Like dissolves like. Okay, but if you want to go into the technical side, then I would say that A, B, D, three of them are three of them have polar bonds, which makes them polar molecule. I think you can understand how the polar molecule is here, right? COH. You can also see in ethanoic acid it's C double bond OH down here. These are polar, and obviously L, there is a double bond down here, so that's more reactive, isn't it? Alkenes are more reactive, isn't? Then alkenes are more reactive than alkenes. That's a proven fact. So there are many reasons if you go into the technical side, but if you want to go into the metamorphical side, like, oh, I don't want to remember that much, then just write like, then just remember like versus like. So if you just find the like molecule any of the option, you can just chok bondo kore. That's the answer. Okay, both of you, did you understand?
Yeah.
Which reagent would convert an alcohol into an alkene? Okay, somebody please tell me. This is very easy. Hmm. Number 10. Which reagent would convert an alcohol into an alkene? Come on. Look, this is where you make mistakes. Use logic. First of all, acidified potassium dichromate 6 is an oxidizing agent. Would you require. Is alcohol being oxidized here? Because if we oxidize alcohol, pretty sure alkene is not produced. We know what happens when alcohol is oxidized. What happens? Carboxylic acid is produced, isn't it? Or another thing is produced, aldehyde. So obviously that will be out of our equation. Gone. Okay, let's move on to anhydrous calcium sulfate. This is a drying agent. Come on. So how can, I mean, this is not a reagent, it's a drying agent. We all know that, right? So obviously that's out of the equation. And I'm pretty sure I've never seen in any organic synthesis where anhydrous calcium sulfate is used, right? It's a drying agent. So drying agent's job is to basically absorb water, not to, oxidize or reduce or do anything else. Okay, this leaves us C and D 50-50 basically. Okay, among this I would say D is incorrect, because if you have check out the organic synthesis processes, ethanolic potassium hydroxide is used in order to do the opposite process, basically to convert an alkene to alcohol. Okay, so D is out of the equation, so the last of obviously this will be our correct answer. Look how I approached with logic with each and every option. Even if you don't know the answer, or even if you are basically confused about this answer, about the answer of this question, there are many ways you can tackle. First one is the elimination method. You basically use logic and judge whether A or B is logical or not. See, I already judged that A B is not logical, so this easily simplifies my answer scenario to C and D. And then you can say the next logic is, we have to choose one. So my logic was that D is obviously, according to my previous knowledge, that it is used to convert the opposite, like from alkene to alcohol. So the only option is left is C, so C is the correct answer. Which is actually, did you understand? So try to use logic all the time if you don't know the correct answer. Ammonia reacts with 1-chlorobutene. State the type and okay. Tell me fast. Easy.
Nucleophilic substitution.
Nucleophilic substitution. That's right. That's right. Yes, exactly. Nucleo. Okay, first of all, type and mechanism. Okay. Type of the reaction is what? Substitution or nucleophilic? Substitution. And mechanism is nucleophilic. Considering a nucleophile is used, right? Who is the nucleophile here? Obviously this one. I believe I have done this. Did I do this? Did I do this question? Hmm?
It's the redox paper.
Yeah, it was in the redox paper. Very good. Samaya, did you check this, the previous video? I think you have seen this question. I've explained it, or do I show you again?
I'm not
Did you see?
sure.
ওকে, কে বলো তো তাহলে আমাকে দুইটা omission কি হবে এই স্টুডেন্টের মেকানিজমে? What are the two things he missed? বলো। না দেখে বলো, চেষ্টা করো লাইভ দেখে এখনই।
Um, lone pair থাকবে
Exactly. So she missed lone pair. Anything else?
and positive charge.
In where? কোথায়?
Nitrogen.
নাইট্রোজেনে পজিটিভ চার্জ থাকবে, যদি লোন পেয়ার থাকে নাইট্রোজেনে পজিটিভ চার্জ কেমনে আসে?
No, no, no. নাইট্রোজেনে থাকবে lone pair
হুম,
আর পজিটিভ চার্জ থাকবে
এখানে থাকবে, এখানে কার্বন অ্যাটমে থাকবে। আরে বাবা, নিউক্লিওফাইল মানে কি? ইট হ্যাজ আ লোন পেয়ার, রাইট? সো ইট
হ্যাঁ
হ্যাজ নেগেটিভ চার্জ। তার মানে কি, সে কি পজিটিভ চার্জের প্রতি অ্যাট্রাক্টেড হবে না? তো সেই ক্ষেত্রে কি কার্বনে পার্শিয়াল পজিটিভ চার্জটা দেখানো লাগবে। এটা কোন ফিশনের মাধ্যমে ব্রেক হয়, হেটারোলাইটিক না হোমোলাইটিক ফিশন? হেটারোলাইটিক ফিশন মানে কি বলতো? হেটারোলাইটিক ফিশন মানে হচ্ছে যখন একটা হাইয়ার ইলেকট্রোনেগেটিভ এলিমেন্ট থাকবে একটা সিএক্স বন্ডে। হাইয়ার ইলেকট্রোনেগেটিভ এলিমেন্ট অবভিয়াসলি হচ্ছে আমাদের এখানে হ্যালোজেন, তাই না? তো এটা যেহেতু হাইয়ার ইলেকট্রোনেগেটিভ, ইট হ্যাজ দ্য কেপেবিলিটি অর দ্য পাওয়ার to you know absorb all the bonded electrons when the CX bond breaks. But what is homolytic fission? Consider C and consider H and Br and Br. Both of their electronegativity is same, right? So whenever the Br-Br bond breaks, both of them will have the ability to take equal number of bonded electrons from their bond. So this is an example of what? Homolytic fission. And these two processes are very popular in a very nice mechanism. Can anybody please name me the mechanism's name? Simra, you are also allowed to say the name of the mechanism where these two process happens. Free radical substitution reaction. Have you heard about it? Is the process in which halogenoalkanes go through, right? So halogenoalkanes go through two mechanisms in our AS chemistry. What are they? One is free radical substitution reaction, and there is another one which is what? Nucleophilic substitution. Now, nucleophilic substitution also has two categories. Do you know the two categories, or you don't know? Nucleophilic substitution has two categories. One is SN1, another one is SN2. Okay. If I talk about SN1 and SN2, SN1 SN1 basically only primary halogenoalkanes. Did I make a mistake? Sorry. So no. SN1 secondary or tertiary halogenoalkanes go through, while SN2 is done by only primary halogenoalkanes. I think you can understand what is the difference between primary, tertiary, secondary, right? Yeah, so remember that. Now, why? What does S means? S means substitution. Substitution. N means I think it's nucleophilic. Yeah, nucleophilic, nucleophilic substitution. And one basically means the first stage of mechanism involves one step. So I think you can understand what happens in SN2. Everything is same, is just that there are two steps in the first stage of the mechanism. Did you get my point? So this is what SN1, SN2 represents basically. Now, these are not vastly given in your AS book. It is provided in your A2 book. So just for your knowledge, you might wanna, just basically do it, and I just remember it. It might come. Then complete the step of the mechanism to form butylamine, showing Carli arrows and relevant lone pairs and reaction products. So I guess it's pretty simple. Who is going to act at the nucleophile? Obviously, our OH guy will act as the nucleophile, considering OH oxygen atom consists of the lone pair. So he is going to get attracted towards the more positively charged nitrogen atom down here. And then what will happen? Can anybody tell me? Simra, tell me what happens in the next part.
it forms H2O.
Mm. Who takes it?
Product is
Who takes the bonded electrons?
nitrogen.
Exactly, nitrogen takes the bonded electrons by hydrolytic fission, and then at last, what happens is pretty
What
simple.
is what?
OH won't react, by the way. Just wanted to let you know. OH is not is going to attack. It's going to attack and provoke the nitrogen atom to take out the bonded electrons from the NH bond, and this will cause the H to come out. This H is going to react with OH to produce two things. Uh, one, acha, there is no. Did you guys take a photo? This side information have you taken? You might want to take this. Have you both Simra Samya taken?
Can you scroll to the top part?
Oh yeah, sure. Done.
Yeah.
Okay, so we can just cut this part down. Okay, so it's going to provoke, and then what happens? The remaining guy will be down here. So that will be this, plus you got water down here. Okay, because OH and H, the guy who came out, reacts with this to produce water. Moving on. I think I've given this answer, so I'm not going anymore. Okay, right? You can, I think both of you saw in the previous classes video, so I'm not coming to this one. Moving on to the next part, which of these isomers with the formula C8H18 has the lowest boiling temperature? Okay, tell me. Three factors have been already discussed a little while ago, so you guys might want to try now. Oh, a minute. Is it correct? A is not the correct answer. Okay. Lowest boiling temperature, they said. This is the highest, so that is out of the equation. Look, I'm using logic. D is not the correct answer. Already I have decided because obviously it has no branch, right? It will have the highest boiling temperature. Second of all, if I move on to the ABC here, B is not the correct answer. Come on, it only has one branch. This leaves us A and C, lowest boiling temperature. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 carbon atoms, and there are obviously 1, 2, 3, 4, 5, 6, 7. There are 7 carbon atoms. Although that there are two branches in both A and C, but the number of carbon atoms is less in this one. So C is the correct answer. Did you get my point? Use logic all the time. Don't guess. The viscosities of four organic compounds are compared by placing the liquids in separate identical tubes, each with an air bubble at the top. Okay, very good. The tubes are inverted and the times measured for the air bubble to travel to. So basically, they're trying to say that when you invert this guy down here, bubble basically comes at the bottom, and then basically the time required for the bubble to travel back to its original position is measured against the length of the tube, which I guess will obviously be measured using a ruler, right? And what will be the time measured using a stopwatch, isn't it? For which compound does the air bubble takes the longest time? Now, this is a nice question, by the way. It's kind of related to physics, I believe. Okay, now can anybody tell me what might be the correct answer? Look, viscosity basically means what? If the bubble, if the air bubble has more attraction towards the liquid molecules, don't you think it's going to take more time to reach its original position, right? So does it has a high viscosity? Yes, it has a high viscosity. But if the bubble basically takes look, so in other words, if time taken is high, viscosity will be high. If the time taken is low, which means that the liquid molecules don't have that much attraction with with the air bubbles, so obviously time will be low because it will take less time for it to go up, and viscosity will be also low. So which compound does the air bubble takes the longest time? In other words, they're trying to say which guy has the highest viscosity with the liquid. So can you please tell me which one? It everything depends on the. Now I have given you a lot of clues. First one is attraction with the liquid. So for attraction we require the production of what? Intermolecular forces. There are three types of intermolecular forces: London forces, then what? Permanent dipole, and then was hydrogen bond. Now question is, what is this liquid, by the way? Okay, we don't know what's the liquid. Forget London forces. Forget London forces. Can I tell you why forget London forces? Because four of them will produce London forces. Gone. So we don't have to talk about that. Secondly, if I talk about permanent dipole, not all of them are polar bonds here. So that won't be. I mean, that is not. That won't be a game changer factor. The only game changing factor will be hydrogen bond. Now, please tell me, where do you think more or less hydrogen bonding will be produced? Now one thing's one thing's clear. You have to understand that D is not the correct answer, because since I already. Okay, C, okay, fine, C, fine, no problem. Why C? Let's come. So one thing's clear, that D is not the correct answer, because D is not going to produce hydrogen bond. Clear? Because simply does not have a hydrogen in with O, or with, what's it called, O. Get it? What I said? Okay. Now A, B, C. Why did you say C? Tell me. Exactly. Very good. So you can produce three hydrogen bond as opposed to two, and here as opposed to one. Okay. So yeah, that's the correct answer. Samaya, did you understand how logical? Look, so many factors here. First of all, you think about the first factor, first logic. Second logic, you talk about what? Attraction. Third logic, you talk about bonding types. Fourth logic, you talk about hydrogen bonding. And fifth logic, you basically now judge who produces hydrogen bond and how many. So this is a step by step process of how you solve MCQs. Do not guess. Do an educated guess. It's a nice word. Educated guess. Okay, let's move on. What is the skeletal formula of 2-chloro-4,4-dimethylhexane? I guess you know what's a skeletal formula. These are skeletal formula. 2-chloro-4,4-dimethylhexane, they said, I believe. Right? So what do you think? Tell anyone.
B.
Why B? Because here 4 4, and then you have 2 down here. Yeah, kind of makes sense. 1 2, so that's not correct. And even if you do, okay, what about this? 1 2 3 4? No, it doesn't make sense. 1 2 3, no. Oh, obviously no. So yeah, A is the correct answer. Sorry, B is the correct answer. Sorry. Some alcohols react with concentrated phosphoric 5 acid H3PO4 to form alkenes. What type of reaction occurs? Okay, alcohols basically reacting with phosphoric acid to form alkenes. I believe a little while ago we did you know question, right? A little while back. Remember this one? Concentrated phosphoric acid. In this question they told you to find the reagent, right? Same thing. A little different. Look, this is how you understand the pattern. In 2022 they told you to what? Recognize the reagent, and here they are now telling you the same. They provide you to the reagent and other clues in order to give a different question, which is what is the type of reaction that occurs. Okay, tell me, what is the type of reaction that occurs? Any idea? Anyone? Hmm? Addition is not correct, first of all. Okay, because nothing is being added here. Okay, so that's gone. Secondly, hydrolysis. Where did water come here? So, I mean, hydrolysis means what? Breaking a product using water. Lysis means breaking, isn't it? So that's gone. Now this leaves us B and D: elimination and substitution. Okay, first of all, you need to check out that substitution reactions are gone through by who? Halogenoalkanes, right? Right, because that's according to our AS chemistry knowledge, this is the only guy that goes through, what, substitution reactions. It might be nucleophilic substitution or free radical, isn't it? Yes or no? So the only logic is, obviously the answer is elimination. Look, this is how you basically use logic. Whatever you have previous knowledge, like whatever knowledge you have acquired, use that knowledge in order to garner the logic and then just give the correct answer. Okay, that's it. Don't need to freak out. The structure of 2-methyl pentanthreol is shown. This alcohol reacts with concentrated phosphatic 5 acid. How many different alkenes can be formed? Okay, nice question. Basically, uh, okay, how many? Elimination here, one thing's for sure. What is elimination? Elimination basically means that here hydrogen will be taken out. Get it? Hydrogen will be taken out. So hydrogen will be taken out from here from the alkyl groups, specifically speaking, because that's what elimination means. Now my question is, how many alkenes can be produced? I think three, because if you take one alkene out, so there is two, so the bond which basically used to form the third hydrogen bond, that will be used to produce an alkene down here and here, and another one I guess here. Yeah, kind of. Did you understand?
Explain the elimination part.
Yeah, sure. 1 minute. I need to show you the elimination mechanism for that. Mm, hmm. This is a nice answer. Let me show you. I think I found it out. Hmm. 1 minute. Check this out. This is a classic example of how, or mechanism of how alkenes are produced. See, this is an alcohol, right? I believe it's something like this. You can see the same alcohol we can see. So what happens is that the H plus from the H3PO4, what happens? So the electrons present in the OH group, we all know that OH contains electrons, like O contains electrons, isn't it? So it's going to attract H plus. Later on, what is going to happen is that this OH is going to break down again. So again, how do you know the OH is going to break down? Heterolytic fission, isn't it? So this, what will happen is that water goes out. So water, I mean OH goes out. So OH is going to react with the H plus present here. Like again, it's the same thing. The H is provoking the OH in order to break itself from the COH bond by hydrolytic fission, and then it's going to react after provoking. It itself is going to react with OH who came out recently to produce water. Now what we are left with, a lot of we are left with a carbocation here. This is the carbocation. Okay, this is the carbocation, isn't it, from where the OH came out. Now this is where a funny thing happens, and it will be out of your syllabus, nothing to do. So first of all, what's going to exactly the breaking down of OH? Fine. First step gone, second step gone, and then you know what happens after provoking the after the H provokes the OH to come out. It basically reacts itself with OH to produce water. Now what we are left with is a carbocation. Now obviously it's a third degree carbocation. Look, this is where things become very nice. If there is a third degree carbocation, then there is possibility that three hydrogens can react. Do you see, like three hydrogens can basically react and produce three different alkenes. Like for instance, beta hydrogen elimination in this is, I mean, if I talk about, this is known as beta. Then if the right side is beta, then you need to consider the, what's it called, these are known as beta basically, and the one which is connected above or below, these are known as gamma. A little bit outside from the syllabus, but this is how it is basically. So these are the carbon atoms, I mean the hydrogens which are connected with the adjacent carbon atoms of a carbon. These are known as beta hydrogens, and the hydrogens which are directly connected with the carbon, these are known as gamma hydrogens. Okay, so beta hydrogens connected with adjacent carbon, and gamma hydrogen connected with the carbon itself. Yeah, carbocation, to be precise, carbocation itself. Okay, so obviously there are two beta, hydrogens, you can clearly see out. So what is going to happen is that both of them have equal amount of chance, as well as the gamma as well. It also has equal amount of chance to react with carbon down here. What's going to happen is, I mean the thing that's going to happen is that hydrogen is going to donate its electron down here, and itself it's going to break down. Okay, here also the hydrogen is going to donate its electron down here, and it itself is going to break down, and same case goes for here as well. So there are three hydrogens, so there are the three possibilities in which you can produce three types of alkene. Okay, one here, one there, one there. Okay, that is the reason I told you that. Look, do you see the carbon down here? Huh? This carbon is what, when this OH goes out from the first step, you can clearly see that there are two beta hydrogens here and there is one gamma, right? I mean, there is one gamma hydrogen. So obviously three of them now have equal chance to basically donate an electron, and 3H plus comes out, and so three types of alkene can be produced. So the answer will be three. A little bit complicated, but I think you should understand, both of you. Did you, Samya?
The elimination.
Yeah, no, I mean, we can just take a screenshot, and I'm pretty sure the recording is there. I will provide you the recording. Okay, no problem. You can check out the explanation as many times as you want. Take a photo. The compound DMAA was originally synthesized as a decongestant. Give the systematic name of compound A. All right, tell me, what is the systematic name of compound A? It's pretty simple. Come on, one, two, three, four, five. It's an alcohol. So is it? Oh wait, is it? And is it? 1 minute. One, two, three, four, five. Oh, sorry, I made a mistake. Sorry. We need to identify the most longest chain here. I believe this is the longest chain. Yeah, this is the longest chain. One, two, three, four, five, six. Whenever you basically write naming, always try to, and whenever there's a branch structure, always try to basically find the longest chain. Okay, so this basically sums up easily. So it's connected with the second carbon, isn't it? So if the second carbon is that, so we already know one, two, three, four. So that's methyl group. So four methyl hexane 2 ol. Okay, did you understand? Sorry, you want to say something? Identify by name or formula suitable reagent for step one. Okay, you're basically converting a what's it called? Uh, Alcohol into what? You're basically converting into an halogen alkane. So what is the reagent? I think you have learned it. Exactly, very smart. PCl5, phosphorus 5 chloride. Give the mechan. Okay, is there any other? Okay, PCl5. Anything else is produced? Do you know when PCl5 is added to an alcohol? We know that, right? HCl is produced. Misty fumes. Exactly, misty fumes. This one come in your unit what? Unit 3. So that's what I said. Give the mechanism for the reaction in step 2. Include curly arrows. Okay, in step 2, basically they're trying to say when you add concentrated ammonia to this, you get what? An amine, isn't it? It's an amine, isn't it? It's an ammonia, right? So that obviously what nucleophilic substitution reaction is gonna take place, isn't it? Hmm? So what's going to? Huh, huh, huh? No, the nucleophilic substitution reaction is going to take place considering ammonia has lone pair of electrons, so it's going to act as a nucleophile. And sure, no problem. Like what's going to happen? Ammonia is going to attack. Okay, tell me who ammonia is going to attack? The chlorine or the carbon? Obviously, the carbon. Carbon. Logic. If ammonia has what lone pair of electrons, it's going to have attack the carbon. A little while ago, we have seen the omission thing, the omission question. Remember? Hmm. So like that, it's going to react with the. It's going to attack carbon, which is going to provoke our little guy here, chlorine, to take the electrons and get broken down. What is the name of this process? Heterolytic fission. Forgot. Then what will be produced? Nothing basically. The ammonia is going to react, isn't it? So the next part is instead of chlorine the ammonia gets added, isn't it? Gone. And then we have our Cl minus here. Now what happens? Look, there is I made a not a mistake basically. Uh, yeah, there must be a plus sign. Can you tell me why there must be a plus sign in the nitrogen atom? Hmm. Exactly. Now, in order to stabilize it, one of our hydrogen here is going to donate its bonded electrons here, and then itself it's going to break out. Okay. So eventually, we get our desired product, which is an amine. Right, while our friend here who went out is going to react with Cl to produce HCl. Did you understand the mechanism? uh, DMMA is only slightly soluble in water but dissolves steadily in hydrochloric acid to form an aqueous solution. Explain the type of bonding that occurs between nitrogen atom and the hydrogen ion when positive ion forms. Okay, tell me what might be between the nitrogen atom and the hydrogen ion, they say. First of all, you need to understand one thing. Hydrogen ion and nitrogen atom. Okay, hydrogen ion has an empty orbital and the nitrogen atom has the lone pair of electrons. So what type of bond do you think gets produced? A dative covalent bond, right? The bond produced between nitrogen atom and H plus ion is a
explain again how you came to the conclusion that it's a dative covalent bond?
First of all, what are the conditions for producing a dative covalent bond? You require one of the atom to have a lone pair of electrons so that it can donate to the other atom, which must have an empty orbital. These are the two conditions, isn't it? So we have here the nitrogen atom obviously has a lone pair of electron, isn't it? Which it can donate to whom? To to the empty orbital. What do you understand by empty orbital, bhaiya? First of all, H plus. H2 থাকার সময় how many electrons are there? Only one electron, isn't it? So what do you understand by H plus? Basically, that one electron which was left, that went out, isn't it? That is why H plus is there. So we have an empty orbital, isn't it? So that empty orbital can be occupied by the lone pair of electron being donated by the nitrogen atom. Donate to the empty orbital of H plus ion to produce the bond. Get my point? So that is it. Dative covalent bond. We understand a covalent bond will be produced, but a special type. That's it. Complete the diagrams to show how the ions form. Oh, this is so pretty easy. What do you think is going to happen? Okay, like this, like this, like this. Is it? I guess. Hmm. Then this. I believe that's how you do it. So can you please tell me who are the small ones here?
Hydrogen.
Yeah, that's how. Negative. Just ensure to provide negative, okay? Otherwise, it will be hard for the examiner to understand. That's H plus, H plus, H plus, H plus.
I think this question they mention in the mark scheme that you have to do the diagrams.
Yeah, yeah, in every type basically. Yes. Okay, up to this much. I think I've showed you a handful amount basically. Okay, let me just show you up to 10th question. This is the last question, then gone. Separate samples of some halogenoalkanes were dissolved in ethanol and a few drops of silver nitrate solution added. The faster the reaction of the halogenalkane, the quicker a precipitate forms. Which of these halogenoalkanes reacts the fastest? Tell, fast. I think you have seen this. Is it?
It's A.
Give me a logic, no problem. Give me a logic, then we'll.
Because fluorine is more electronegative. It's going to be bonded to the hydrogen atom. Yeah.
Look, how? What do you think the reaction time depends on? The reaction time depends on the carbon halogen bond strength, isn't it? The rate of reaction basically depends on the carbon halogen bond strength, isn't it? Right? So if the carbon halogen bond strength decreases, the rate of reaction is going to increase. Why is that the case? Can you please tell me? Yeah, exactly. So please tell me, who do you think the rate of reaction? I mean, like, tell me now. Who do you think then? A. Fluorine, chlorine, bromine, iodine. Now, what does the bond strength depends on? To what? Sorry.
Electronegativity of the atom.
Exactly. Very good. So fluorine, chlorine, bromine, iodine. Oh, we all know what is happening as we go down. Electronegativity increases, right? So A is the correct answer. Which of these halogenalkanes reacts the fastest? Oh wait, it's the same and same. Yeah. Oh, tell again. Okay, now this is a little bit different because look, the fun fact is that here the halogens were different, but here the halogens are not different, so we can't consider the carbon halogen bond strength here because the carbon halogen bond strength is kind of same. The only thing that's different, it depends on one is primary, one is tertiary, one is secondary, one is tertiary. So now tell me, which one do you think reacts the fastest? Okay, okay, as far as I remember, that tertiary takes the fastest to react, then comes secondary, then comes primary halogenoalkane, right? So if that's the case, fastest, obviously the our answer, what our answer won't be D, because it's a primary. If I talk about what CBA, if I talk about A, okay, C down here, uh CHH, uh CH2BR, then C. So that's what, secondary, right? No, it's tertiary, isn't it? Hmm?
Yes.
No, 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 no. I made a mistake. No, no, no. Ah, I making a mistake. Okay, that is not correct, because that's something else. That is primary. Okay, so B and C is a little bit. Let's see. So C. If I check out B, C, BR, CH3, CH3. Okay, that's tertiary. And if I check out in this one, I'm not. Is it correct? CH3. This is tertiary. So C8. Then with this C, I guess CH2BR. Uh, ah, this is second. No, primary. This is primary. So the correct answer will be C. Yeah. No, 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 not C, not C. Sorry, B, B, B. Yes, because it's tertiary. Okay, it makes sense. Did you understand or not? Look, it depends on the halogen carbon bond. Are you understand?
So not tertiary.
How is it not tertiary? I mean, look, the Br which is connected with the carbon, it's only attached with only one carbon atom. So obviously it's primary. But if you check out in this one, the Br with which the carbon is attached, it is connected with one, two, and this one, the branched. Samaya, did you understand? Okay, that's it basically. Up to this much for today. And yes, 1 minute. Let me check. Please check out the WhatsApp. Did you guys get the uh, what's it called? The PDF organic chemistry. Did you get it? Both of you?
Yeah.
Okay, so I think I did up to question number up to page 12. Okay, do the others and our submission. When do you want the submission? Next week, I believe. Next week. Next week. Next week it's going to be on, what's it called? Uh, when is our next week class? 30th. Yes, 30th. Next